How do you stretch space? In Euclidean plane geometry, we have the Pythagorean theorem that applies to right triangles. A squared plus b squared equals c squared. In right triangles, we also get trigonometry, the trigonometric ratios sine, cosine, and tangent. Also with triangles, we get that the sum of the interior angles is 180 degrees. So when we talk about the Cartesian plane, we're giving coordinates to the plane. A point xy is a coordinate, and the distance between 2 points can be found using the distance formula. We can also find the slope of a line, which is the ratio of the rise over the run, or the horizontal and vertical length ratio. This helps us define the equation of a line y equals mx plus b in slope-intercept form. When we combined right triangle trigonometry and the Pythagorean theorem, we get circle geometry. So describing a point on the circle, x squared plus y squared equals the radius squared, equation of a circle. It's really the Pythagorean theorem at work. If we apply the trigonometry to the right triangle embedded in this circle, we can then define coordinates x and y in terms of sine and cosine. This is sometimes referred to as polar coordinates. Now, vectors in the plane, defined by the components and their basis vectors, are things that have both magnitude or length and also an angle that indicates their direction. Magnitude is found in the natural way using the Pythagorean theorem. So since vectors have both length and direction, we have two parts to pay attention to: the components that encode length and the unit basis vectors that encode direction. The unit basis vectors live along the axes. Now, vectors in three-dimensional space consist of a linear combination of components and basis vectors. Vectors in three-dimensional space work pretty much the same as vectors in two-dimensional space. There's an added basis vector, k hat, which goes along the z direction. Recall that the equation of a line is y equals mx plus b, where m is the slope and b is the y-intercept, or the starting point on the y-axis. Alternative forms for the equation of a line include the point-slope form, given a particular starting point which may not be on the y-axis, or the general form of the equation of a line, ax plus by plus c equals 0, or alternative forms of this, where a, b, and c are constants. Curved lines in the plane are described by equations given by polynomials or other types of functions. F of x is usually used to describe a function. So given a point P on a curve, we can define a line tangent to that point on the curve and describe a tangent line, which would describe the straight path a point on the curve would travel. Since the curve pulls away from a straight line, we say that it has curvature. Bending and stretching space is all about curvature. A line in three-dimensional space can be described by a vector equation that looks like the equation of a line. So starting with a vector b, like the starting point or the y-intercept, b is a constant vector that points in the direction of a coordinate point that lives on this line. Now we need a vector that is parallel to this line, let's call it vector a, and if we are going to describe moving along this line, we need a parameter t to include, so the line is given by the equation at plus b, just like mx plus b. The variable t is called the parameter. what about the curvature of a surface? The simplest surface in 3 dimensions that we can describe is a plane. AX plus BY plus CZ plus D equals 0, or an alternative form of this equation describes a plane in 3 dimensions. Now in geometry, typically we define a plane by 3 non-collinear points that are 3 points not on the same line. That gives us 2 directions to work with. Think about this like length and width. So some plane sitting in 3-dimensional space will have 3 points non-collinear to it living on that plane, and we can define vectors for each of those points on this plane. So if we consider this plane in 3-dimensional space determined by points P0, P1, and P2, our non-collinear points, then the vector equation for this is given by the normal multiplied by one of those tangent vectors. So we imagine this plane as a tangent plane, and we'll discuss more on that a little bit later. A normal vector will always be perpendicular to this plane, and so we can use the 2 vectors P0, P to define such a normal vector and to define the plane itself. This is typically sometimes referred to as the point normal form, and it should look something like the equation of a plane. The normal components, A, B, and C, would form the coefficients for the plane that we're trying to describe. So let's create a normal vector in 3 space. So from the vectors that determine the plane, that is, the vectors that live on the plane, those 3 points helped us define those vectors, we have components to work with. Using the determinant with the basis vectors and the components of the vector, we can define the normal vector, because this is how we define the cross product of these 2 vectors. In component and basis vector form, we see the components and the basis vectors defining the normal. And in component form, whatever numbers we get from those will be the plane coefficients. Given 3 non-collinear points, P0, P1, and P2, find the equation of the plane that they are all on. Our first approach is algebra. So, using these coordinate points, we can set up a system of equations, a 3x3 system of equations. That is 3 equations and 3 unknowns. Well, actually, in this case, 4 unknowns. But we'll see how to deal with that in a moment. Now to solve this system, we can perform a few row operations, and there's a few approaches you can take with this, but what the row operations amount to is that you take an equation, which is a row, and you multiply it by some constant. You then add that to another row, and that gives you a new equation to replace that row with. So as I'm going through here, I'm trying to use what's called the elimination process to try to get the number of variables in each equation, the number of unknowns, down to as small as possible. And so as I've gotten it down here, we can now define or let D, that variable, become -7, which will allow A to be 1 and the coefficients B and C to be -4, -3. And we can write down the equation for a plane. Seems pretty straightforward, but let's take a look at a geometric approach. So imagining these points as the vectors on that plane we talked about earlier, the vector plane equation is the normal multiplied by a tangent vector, a vector on that plane, will always give us a dot product of 0. So here's our plane. Here's a few vectors on that plane defined by the 3 points, P0, P1, and P2. Let's call them tangent vectors for now, but they're just vectors. And these vectors on the plane can be found by finding the difference of their coordinate point values. So we can find the components of each of those 2 vectors on the plane given the 3 points. Next, to find the normal vector to that plane, we just simply find the cross product, and that amounts to taking the 2 vectors we just found with the basis vectors and finding the determinant. The determinant produces a new vector. That vector is a normal vector that points perpendicular to the plane. It points off of the plane. So now the normal multiplied by either one of these vectors in general form will be able to give us the equation of a plane. So I chose point 0 to work with here and use that to define P0P. And with the normal vector we just found, the dot product is always equal to 0, will produce an algebraic equation that describes the plane. And with a little bit of simplification, we get the form of the plane here, which looks similar to what we found earlier, but we're going to have to do a little bit more simplifying to make sure that it's exactly the same plane we described earlier. So using the distribution property, we will wind up getting the plane that we found before after collecting like terms. So that's our equation. Lines are straight. What about curves? Lines and planes are flat, meaning straight. Rather, polynomials tend to be curved. And so we can use polynomials to help us describe the curvature of space. So, given a point on a curve, the tangent line is something that describes a straight path, and calculus helps us describe what the slope of that tangent line is. df dx is the f prime is the derivative of the curve at that particular point. It describes how fast, or the velocity of how fast something's moving along the curve. So if f of x is the position, the first derivative is the velocity of the curve. How fast something's going along the curve is the slope of the tangent line, the straight line path that point would follow. And acceleration, how fast it is accelerating, is given by the second derivative. And that's a measure of the force needed to stay on path to that curve. So acceleration is actually a measure of how fast that straight path is changing or pulling away from the curve, or how fast the curve is pulling away from the straight path. So curvature has to do with circles tangent to a curve. Now consider a circle of radius r tangent to a curve, and remember from geometry that a tangent to a circle is always perpendicular to its radius. So the tangent vector and the radial vector are perpendicular. Acceleration, due to this curvature, always points towards the center here. And the magnitude of acceleration looks to be the same as the length of the radius. Now, if at a different point we tried to find the curvature by measuring the circle and its radius of curvature, we see that here we would have a larger radius, a larger circle. But the curve doesn't bend as extreme over here, so it's a little closer to being flat. And therefore there's an inverse relationship between the curvature and the radius of curvature. We can explore this further by taking a look at some parametric equations describing a circle. So describing a circle with parametric equations, as we had talked about before using trigonometry, we can describe a path around the circle by picking a particular domain or a set of values that the parameter is going to take on. Here the parameter is theta, an angle, and we're going to allow it to value between 0 and 2 pi. That'll create a full circle and no more. We'll trace out a full circle. If we went past 2 pi, it would start retracing that circle. So the circular path is what we're going to name as gamma, that Greek letter. A tangent vector to a point moving along this curve will be given by the derivative of those parametric equations. And we see that the tangent vector is always going to be, well, here it is perpendicular to the radius, as we would figure would be for a circle. The second derivative, as we defined earlier, was the acceleration of what a point would be moving around that curve, and the acceleration vector is perpendicular to the tangent curve, even if we give it to be at the origin. So the acceleration vector, actually, if we look at it, is just simply the negative of the radial curve. That means that it just points in the opposite direction of the radius. It points inward towards the center. the acceleration is pointing towards the center of the circle. That is an instance of measuring the curvature of that curve. Since we have a curve, it pulls away from a straight line. The length of that acceleration vector, since it's a vector, we can just use the length formula for this. And we see that once we work out the details, that the length of the acceleration vector is the same thing as the length of the radius, as we should have expected. But it's a constant, so that means that acceleration here is always constant. The curvature is always the inversely proportional relationship between this radius, so we would say that the curvature here is 1 over the radius, 1 over the length of that acceleration vector. And that's pretty heavy stuff. Surface curvature. The curvature of a surface, since it is two-dimensional, requires two directions, and those directions are defined by what we call the unit tangent vectors. They're the vectors that live on those planes. And so a normal vector, as you recall, is a vector that's perpendicular to both of these, and it points off of the plane. In a sense, it gives us a direction of up. So 3 non-collinear points, or 2 non-parallel vectors, help us define a plane. And with those 2 vectors, we can define a normal vector perpendicular, so we can define 3 directions in space relative to the surface of perhaps anything we want to investigate. So the basis vectors will always have unit length. Those are in the direction of, let's say, x, y, and z, or in this case, u, v, and n. And a unit vector is just of unit length by dividing any vector by its own length. You just have to take a vector, divide it by its length, and it's of unit length. The cross product of the 2 tangent vectors on the plane give us a normal vector. This is using vector calculus. Now, the unit sphere comes into play here for surface curvature because we compare the curvature of a given surface to the surface of a sphere. A sphere has a lot of radial symmetry, so we can use it to our advantage. The Gauss map, or the normal mapping, takes the normal vector from a particular surface and will take it to the surface of the unit sphere. So let's explore this idea a little bit further. Curved surfaces will have a tangent plane, just like a tangent line, defined at each point on its surface. That tangent plane is defined by 2 non-parallel vectors, 2 tangent basis vectors. That also allow us to create normal vectors, the up direction from the cross product. And that's a determinant type of thing. Now, the key idea is that a normal vector to a curved surface at a point can be mapped or transformed over through a function to the normal vector to the unit sphere. That is, imagine a flat plane sitting on top of a ball and the arrow that points up off of that plane. So the normal map is called the Gauss map, named after Carl Friedrich Gauss, one of the greatest mathematicians of the 19th century. So when we take the normal vector from a surface, any surface, that lives on the tangent plane, and we map it over to the tangent plane that lives on the unit sphere, we get the normal or Gauss mapping. Now, what's really critical here is that if we differentiate this map, that is, we apply a little calculus and take the derivative of this mapping, this function, it creates a 1-to-1 correspondence. That is, the mapping between the tangent planes is a linear map. That helps us out, this 1-to-1 correspondence, in defining an inverse map, which helps us go back and forth between the 2 tangent planes. So surface curvature is a definition of the 2 principal curvatures multiplied together. That is, in one direction, let's say the x direction, there's a curvature measured, and in the y direction, there's another curvature measured. And along those 2 directions, we take the product of those 2 curvatures, we'll call them kappa 1 and kappa 2, or k1, k2, however you see it, And the Gaussian or surface curvature is just simply the product of these two numbers. What's really going to be a takeaway from here is what is the sign of these curvatures that is going to define the surface. A surface with zero curvature is considered flat like a plane. Negative curvature called hyperbolic, and positive curvature is called elliptical or round. There are some other special cases. Now, if we pick a point on a surface, the differential of the Gauss map, as we discussed earlier, is a linear map, a one-to-one mapping. And the Gaussian curvature is actually not only the product of the principal curvatures, but it is also the determinant of this differential mapping. In a similar case, we can define something called the mean curvature or average curvature of a surface, which has to do with the trace of the differential mapping. The curvature of a curve, gamma, is the length of the acceleration vector, the second derivative of the curve. It's inversely proportional to the radius of the curvature. Surface curvature is the Gaussian curvature. It's the product of something called the two principal curvatures, which are in the principal dimensional directions. In higher dimensions, a surface is referred to as a manifold, M. It can have an arbitrary number of dimensions, so we say that it is n-dimensional. And a coordinate point in this manifold is given by n different coordinates. The length of such a vector in this space would be given by the square root of the dot product, length in n dimensions. So Bernard Riemann took the idea of curvature to higher dimensions and equated the curvature of geometric space to forces of nature. Force equals mass times acceleration, and recall that the acceleration, or at least the length of the acceleration vector, is how we measure curvature. Riemann claimed that gravity was due to some sort of curvature in a fourth dimension that we experience in three dimensions. For a two-dimensional surface, you can assign to each point in space, well, a collection of numbers. Three numbers, really. And those three numbers completely describe how that surface, that two-dimensional surface, will bend or stretch in space. Riemann found that in 4 dimensions, one needs exactly 10 numbers to describe the curvature at each point in space. That fourth dimension is time. The numbers that describe the bend in space are numbers given by something, a collection of numbers actually, called the metric tensor. It's a way of measuring lengths in higher dimensional space. It's a collection which we would know as a matrix. The Riemann metric tensor and the general metric tensor that measures all of the things in higher dimensional spaces, they work on manifolds, and the matrix is really 16 numbers, but 10 of them are independent due to some symmetry among the elements. So it looks something like this, a matrix of entries 4 by 4, since it's a 4-dimensional space. And each one of these numbers would represent some type of measure of curvature in the space. So Riemann developed his own curvature tensor, which is pretty complicated in n dimensions. It has a number of indices that you have to pay attention to. Now, although Riemann was convinced that his tensor described how physical space bends and stretches, he really didn't know what the mechanism by which made the space bend. That was something that will have to lead up to Albert Einstein. The Einstein field equations make use of a few different tensors, one of which is the Ricci tensor, starting that up, r mu nu, and that is a measure of how volumes change throughout space. The Ricci tensor is really the trace of the Riemann tensor as a matrix. Now, calculating how volumes change allow us to say how the space is being stretched. Also, because of conservation laws in physics, there's a couple of correction terms, and you'll see the metric tensor being used here, g mu nu. Capital lambda is the cosmological constant, and it accounts for the fact that the universe itself is expanding. Space is expanding. On the right side of the Einstein field equations is the stress-energy-momentum tensor, and that connects matter or mass to y, the mechanism, what makes space stretch. Now, Einstein made the breakthrough of connecting that mass or matter, that which was also governed by gravity, was the mechanism behind the stretching. That space and its curvature tells objects in it how to move. That matter bends space. So what happens if you get enough matter into a small enough space? Then what happens? General relativity predicts that if enough matter is condensed into the smallest radius, then it will collapse into something called a black hole, a place where space and time stretch so quickly, faster than the speed of light, that not even light can escape it. It's a point of no return. Now, Einstein's equations allow for perhaps a bridge through space to be created, building on something that Riemann himself actually considered, something called a Riemann cut, or considering multiply connected spaces. Now that's the stuff of science fiction. Hey, I'm Doug. Thanks for watching, and join me next time on Figure It Out.